Hello and welcome everybody to the presentation of our paper towards a platform and benchmark suite for model training on dynamic datasets. This is joint work with EuroMLSys'23, Viktor Gestager and Anna Klimovic. I'm Maximilian and I'm happy to present to you today our ideas on why dynamic datasets are important, what they actually are, and why we have a vision to build a platform that enables model training on these kind of datasets. To introduce the use case to you, imagine that you run some form of grocery delivery service which runs a recommendation system. And this recommendation system suggests users to buy a certain type of food. Now suddenly on social media there's a big trend to bake banana bread, for example, due to a pandemic. So you probably would like to recommend bananas, butter, maybe even a recipe to your users to make them buy these kind of groceries. However, you only do this if you update your recommendation model. And for this you need to pick up on the latest trends. Maybe people have already started to buy more bananas and you want to incorporate and reinforce this into your model. And this is why the basic claim behind dynamic datasets is that we need to update our production models. This is the core idea. Models are not static, they are instead dynamic. And this kind of retraining or model updates really do matter. So here you see an example from a study from Grubhub, and they show if they make suggestions or recommendations based on like more frequent training data or more recent training data, the purchase through rate, which means how many people buy something after getting a recommendation, increases by a huge margin. So like daily retraining leads to a 20% higher purchase through rate. And this is why we introduce dynamic datasets as datasets that change over time. This means that there is a notion of time datasets can get added or removed from the set. And we think there are three main reasons for why this might be the case. So the first one is that you just collect more and more data. Imagine autonomous driving, where you have vehicles that continuously take pictures of streets and so on, and you would just want to incorporate all of this new information into your autonomous driving model. The second thing that might occur is distribution shift. So here you see a yearbook from the 1920s and from the recent years, and obviously there's like a trend change in hairstyle. So if you want to make some classifier based on this data, it probably will perform worse if you trained on past data. Last but not least, you have something like GDPR that allows users to have their own data deleted from your models, which means that you have to also unlearn the data points. So this is like a whole research direction in its own, but this also makes your dataset change over time. And if we consider what datasets we currently use in ML research, right, it's MNIST, CIFAR, ImageNet, it's all very, very static. There's no notion of time, there's no distribution shift, and this is why we say there's a gap. There's a gap between research and practice when it comes to the type of training data that we use. And when talking to industry, so we talked to like some industry colleagues and got like some ideas on how they tackle this problem, and we see that it really is common to fine-tune and retrain your models. But everybody is just, being a bit hand-wavy about this. We maybe retrain on here, we fine-tune there, we do it every week, we do it every day, because some engineer just like randomly decided to do it like this, but they never evaluated these kind of decisions, and we just don't know what performs best. And this is why we say, there is a big research scope here to explore. And if you consider the cost of these retraining options, right, it's getting more expensive the more data you collect and also the more frequent you retrain. But like the general idea is, the more data and like more frequent I retrain, the better my model will perform. So the question is, can we make this more efficient? And this is the main research question we want to address with Modin and our work on dynamic datasets, is how can we lower this cost, right? It's not really sustainable. From an economic perspective, you can also think about it ecologically, running all these GPUs all the time. Like, can we reuse basically past computation to make model training more efficient? And for this we identify two main dimensions. The first question that we ask is, when do we trigger a training? Like, when do we retrain? Do we do it every week and so on? And the second question is, what data do we train on? So both of these questions directly correspond to the cost of retraining I just discussed. If we could train on less data, then obviously the cost of training will go down. If we train less frequently, the cost of retraining will go down. The question is, can we do this while still keeping the model performance? For the first question on when we want to trigger training, we have identified 3 main triggers that people currently use or that could be used. The first are amount-based triggers, which means triggering every n data points, like every 1,000 data points, every 10,000. If you collect a specific amount of data, then you run a retraining job. The second is time-based triggering. So with time-based triggering, you say every day, every week, you want to run a training job. The last thing that we've seen is drift-based triggering. It's not really done in industry yet from our discussions, but the idea is that you can use some form of drift in your data distribution to be a bit more informed about like when do we trigger a training. So for example, if your input distribution changes a lot, like in the yearbook example, you might want to retrain instead of like every week. You just might, like in COVID times, you might do it every day, and after COVID, you do it every month. So just be a bit more informed about it. You can also consider a different proxy for data drift, which is your inference pipeline, right? If your model inference performance degrades over time, so for example, your recommendations are less and less good, people are not purchasing as much anymore, then you might also want to consider running a retraining job. And for the second question, what data do we train on? The question really is, can we identify an important subset of the data? And with important, we mean that we keep model accuracy high, but want to reduce compute. And we really want to stress the important data part here, because it's actually a very difficult question, like what makes data important? So consider this time arrow you see right above me here, and this yellowish thing. There it is. So this is our reference point for our time. And now if we consider a very old data, then we may ask the question like, is this actually still important, right? It's very old, maybe it's outdated, but maybe if we consider Gaussian, you can still infer the mean from the distribution, and just the variance has shifted a bit over time. Maybe there's still some information in this past data. Maybe it's also completely outdated. And like if we now come closer to our like orangey reference point here, then still the question is now, this is more recent, is it important? But maybe also like this was a lockdown week, right, where lockdown measures were announced, so everything was very changing. There's a lot of distribution shift going on, but it's just not relevant anymore, even though it might be more recent, right? So the idea from this slide really is time might be like a proxy for importance, but not necessary. Like maybe all data is very important, and the 1 week where a lot of news were going on caused lots of disturbance in your data, but actually like from a longer term perspective, that's not really important. So if we consider what prior work has done for data importance, we see static data sets and dynamic data sets again, like different types of policies that we see. And for static data sets, these are terms like core sets, data distillation, data valuation, and these policies were really built like without dynamics in mind. And this is a problem. We can I can refer to our paper for like an explanation why this is a problem. But in a nutshell, if you consider, for example, model loss as a proxy for importance, then again, if the loss is high on all data, which is just outdated, we would consider this as important data, even though it's just outdated and therefore from a different distribution. And on dynamic data sets, on the other hand, the research stream of continual learning, which is a bit, goes a bit in a different direction. They focus on learning new classes over time, while we really care about classes changing over time. Like you still have, for example, bananas or users, but they just have a different behavior, a different distribution, which is why these policies might be useful here, but are not really tailored towards our setting. And so the answer to the question is, how well do these policies perform? We don't really know empirically. I've explained to you why they might not work. Maybe they also do work. The thing is, we just don't know. And in order to find out like how they work and if they perform well, we think there's a need for an open source platform that enables you to test these different types of training and data selection policies, that enables management of these dynamic data sets, and that also just orchestrates like these multiple training jobs. And also we think there's a need for a representative benchmarking suite, because there are like some papers proposing benchmarks for data distribution shift and so on, but not really for the setting of dynamic data set and retraining and so on. And the question, why do we need a platform, is like the next natural question to ask, right? Why not just build a Python script? And the problem really here is there are billions of samples in these data sets. So for example, in the Criteo DRM dataset or Criteo recommendation model dataset, you have 24 days with 180 million samples per day. And just if you think about building a data selection policy where you assign each sample an individual key, you suddenly have billions of rows you might want to insert in a database and so on. You suddenly have a data management problem. It's not really just scriptable anymore. The orchestration of training jobs is not really trivial, right? You want to continue training on the previous model, you need to start more jobs and so on. So for this you need different components, and like at this time you already see you're arriving at something that really resembles a platform. And also a platform enables us to do systems research, which we as systems researchers are also like interested in, right? Can we optimize storage for data selection policies, for example? Like, can we optimize prefetching? What are the knobs to tune to improve the system performance? Enter Modin, which is our vision to build a platform for model training on dynamic datasets. And next I'm going to introduce the like structure of Modin that we currently have in mind. It's still work in progress and we are open for collaboration, for input on this. But in general, the idea is that you have a data pipeline somewhere, and this is where all the data filtering, cleaning that you do once happens, right? This is out of scope of Modin. And at one point you might want to sync or output your data into Modin's data storage component. And this data storage component then like is the base where every data is stored, and the supervisor, like the heart of Modin, will then be accessed, will then access the data storage. So the engineer really first of all configures a pipeline at the supervisor side. The pipeline is the core unit of execution in Modin and collects like all the hyperparameters that we need to define the pipeline, like the training policy, the triggering policy, the model, and so on, all the hyperparameters. So you have data and storage, you have the supervisor, and the first thing that happens is that the storage sends the samples to the supervisor, which implements the triggering policy. And also the supervisor forwards it to the second most important component in Modin, which is the data selector. And this implements the data selection policy, as in the name. So we got the supervisor for the triggering, we got the selector for the data selection, and now really the supervisor makes a decision to trigger training. At one point, like after a week, after a million data points, after data drift, the supervisor will make the decision to spin up some training job. And for this we have the trainer server, which really is an abstraction where we can send like a job to train this model on this data with like continue on the previous model, and all these types of hyperparameters that we need to orchestrate basically. For this we go to trainer server, and the trainer server has something called a trainer, which spins up on request, and the trainer as a first step really requests the training set keys. And then with this set of keys that the selector has decided to train on, we go to storage, fetch all the payloads. Of course, like communication and computation is all interleaved, but conceptually we fetch all the payloads, and then on the trigger we start to train on these data items. And in the end, maybe we want to collect some metadata on like loss as a trigger for importance or something like this. So we might want to, this is like basically the metadata collector, and in the end we output a trained model that we can then use for like production use or for evaluation, or to continue the training on. So this is really architecture of Modin, and these two components, the supervisor and the selector, are really heart of Modin, with the supervisor being the coordinating part and the selector being like the informed part that cares about what data we train on. So to introduce like one example use case, again, it's recommendation systems. We train a DRM recommendation system model on the first 10 days of the Criteo dataset, which I already briefly mentioned, which is a prediction dataset for advertisements. It's pretty commonly used, and it's a really interesting benchmark for the modern system because it has so many samples, right? This is really a stress test to test the infrastructure. What we do here is we continuously fine-tune our model in this very basic example and evaluate on a 10th day. So we train on days 0 to 9 and we evaluate on day 10, and in the best case the more recent data performs better. And this is the plot. Again, here on the axis you see the days that we train on. We evaluate on day 10. We care about the accuracy under curve, which is a common evaluation metric for recommendation systems. And here you can see the line. So it doesn't look like a lot, but the trend does go up. And if you take a look, if I step in the other direction for a second, there's an Alibaba paper saying that really small increases in accuracy under curve can lead to a 1% revenue increase, which really can have an impact of millions and billions of dollars, right, in your company. So these small changes do matter, and obviously this is just an initial experiment. We are still working on mode and to explore this type of questions, right? What works better? Retraining would mean training on even more samples. Here we fine-tune. The question is how do they compare and so on. So these are questions we want to explore, but this really shows that modern is currently a functional prototype. And we are also building another this benchmarking suite in addition to Criteo, right? For example, we can use Reddit data for text classification over time. Autonomous driving is a use case I already mentioned. That is interesting because there is no distribution shift and you just collect more data. And also weather forecasting is interesting because climate models get updated, collect more data, more recent data, climate change, all these trends that you might want to incorporate into your model. So this is use cases that we currently explore. If you have any use case that might be interested in the setting, we are more than happy to integrate it in the benchmarking seat. Again, this is work in progress, and we try to figure out something that covers many different use cases, many different models, and so on, to find something representative. So to conclude, again, in practical deployments, data is dynamic. This is our core observation. And the problem is that right now we do a lot of retraining, fine-tuning, which is not sustainable because there's just so much data, even bigger models. You cannot run petabytes of training data through a billion parameter model every day. And this doesn't work anymore. And this is why we propose to build Modin, which is our work in progress prototype, to explore the question of when to train and on what data to train. If you're interested, I need to figure out again. Yeah, this is the GitHub link where you can see our current code. Again, we are happy to collaborate on this. And yeah, if you have any questions, please message us. We are always curious to chat about ideas and what might be interesting in this context of streaming, machine learning, dynamic data sets, and so on. So we are more than happy for feedback. Thank you so much for your attention, and have a nice day.